Zoom. All right. I think we left off right here. Here. All right. So let me erase all of this writing, and I'm gonna cut these problems out so we can work on them. That's it. I'll just cut the whole thing. Copy that. I don't caption, man. All right. So let's take A. We're going to start out with A, and A is kind of, I won't call it tricky, but the reason, one of the groups that I talked to when we were working through A, I think the dying kind of threw it off, right? Because the dying, we used to seeing it written as cis. If you ever see it written as trans like that, all you have to do is switch it over, right? Unless it's substituted in such a way that the S trans is not possible, which I'm gonna show you on one of these questions shortly, right? So we're gonna take that diene and just write it like this. There's nothing stopping you from doing that. If you ever see it written in an S trans fashion, just turn it to S cis, right? And then that's going to be plus, we're going to say, this is my diene file. I'm going to write that like this. Now that ring, I can abbreviate as PH, right? Come on, Russell, get it together. It's a phenyl ring. So I'm going to just abbreviate that as PH. So then after that, now you can see where you can number and put the arrows in, 2, 3, 4, like that. And that's 5 and that's 6. Right, you can see that right away. So now I just need to push arrows here, here, and here. And so my product is going to look like this. All right, and then I'm not gonna define the stereochemistry of that phenyl group. I'll just leave it undefined. But you do, and we already discussed this, that stereo center right there, it can be up or back, right? You're going to get both products. For B, same thing. All right, we already have our diene written. It just happens to be substituted with methyl groups like so. All right, so that plus I'm going to abbreviate that ester 2. All right. So these are my 2 star materials. What do I need to take into account in this question as it relates to the diene file?
Substituents, right?
Yeah. What's the conformation or the stereochemistry of that alkene? Is it cis or trans?
Trans.
It's trans. Good. So my product, which is going to be a 6-member ring, it's going to have an alkene here. These, come on, man. Here, substituted. And then on this side, we have, zoom in so I can write that better. I'll zoom back out in a second. We have this. And then this chlorine, right? It's trans. And you know, because you don't have a bias, you don't have anything that's going to favor one of those stereoisomers over the other, you're also going to get the other stereoisomer, right? Where the chlorine is on a dash and the ester would be on a wedge, right? So this right here, all this spinach, right? You can write that as, you can combine those oxygens. So CO2, I just put a methyl, Me, instead of CH3, or you can write it like this. Right, it's all the same thing.
Dr. Russell,
Yes.
so for the first one that you did the stereochemistry, did it change from trans to cis?
On the first one right here,
Yes.
there's no stereo. Well, that alkene is monosubstituted, so it doesn't. You can't call it trans or cis.
Okay.
But in the product, that ring, that phenyl group that I have out here, that's actually that benzene ring. I can write that as. Let me see if I can erase that without erasing everything. Yeah, I can write it like this, or I can write it like this.
Okay.
Right. But I just left it undefined, but I'll go ahead and write the other product in. But it's not trans or cis because it's a monosubstituted
Talking
alkene.
about like not the product side, but the first part, like how you drew it as a cis.
Oh, this right here. You mean the diene?
Yes.
It's S cis. Yeah. All right, so S cis. Right. But up here, and where the problem first, where we first encounter it, is written in the S trans conformator. Okay, I got you now.
Okay.
Right. And that is important. Remember, we talked about that. If it's S trans, then it can't overlap in the transition state properly. So it's got to be written as S cis. But that's that's why you heat it, right? Because that's where the energy comes from for it to convert or interconvert from S trans to S cis. Because that's the only way it can react properly.
Okay, I understand now.
Mm-hmm. Yeah, I'm sorry. I misunderstood what you were asking. But yeah, I changed it so that I can write that out. All right. What about, so that was B. Let's look at C. C is really the same thing, same problem. So I'm gonna cheat. I'm gonna cheat a little bit. So this is C, but the difference in C, you can see immediately when you look at that problem, is that the dienophile is now cis instead of trans, right? So in the product, that means that those groups, I'm gonna cheat again, are gonna be cis, right? And the other, well, for this one, the other enantiomer won't matter because it's symmetrical. Well, no, take that back. No, it's not. So here, the other enantiomer will be here, right? You're going to get both. Right, so you'll get both enantiomers.
Wait, why are you? Well, I was gonna ask, why are you getting both enantiomers? Like,
What's stopping one? What's favoring one over the other? Like, there's really no difference between them, and that's because what I start with, my start material, I don't have any way to create like a bias. I don't have a chiral catalyst. I don't have a chiral starting material. So it's going to be a racemic mixture. And the fact that both of these are stereo centers means that I'm setting stereo centers in the product, but I have no way to control like which one of those isomers is favorite. So you're going to get both.
Okay.
Mm-hmm. All right, let's look at the last question, which is F, and we're going to do the same thing for F. We're going to turn that alkene, the diene from S trans to S cis, right? And it says excess, and you know that's not there on by happenstance. Plus this, I think this is the right thing. All right, what do you think? Why do you think that's saying excess?
Could it be because there's more of a diene than usual? Like, I don't know if that makes sense. Like more of maybe like another diene, or like it's a heavier diene. I don't know.
Not quite. That's a good thought, but it's not quite that. Let's think about the reaction itself, right? What is that diene reacting with?
You said what is it reacting with?
Mm-hmm. What's the other part of the dienophile, which is this right here? Is that right?
Yes.
What part specifically of the dienophile is it going to react with? It's not going to react with the carbonyl, right? It's going to react with the alkene right
6
here.
and 5.
Mm-hmm.
Yeah, the alkene.
So do you see that same alkene? Is there more than one? Isn't that same alkene over here as well? So you actually have two dienophiles present.
Oh, okay. Because
You
there's
see
two
it?
alkenes to the dienophile, so there's actually two dienophiles.
Right. So you got to add more diene to react them both. That's why this is present in excess, right? It could have been written with two equivalents, right? So 2.0 moles to 1.0 moles like that. And then that would simplify it. But the fact that you got two dienophiles, two potential dienophiles, that's all this question is asking, right? So
sorry.
go ahead. No, go ahead. I like excitement.
So if the dienophile has if there's two dienophiles, what does that have to do with the diene? Is that because it's attacking two of those dienophiles?
Yeah.
So it's labeled excess?
Yes. So you want to add more diene so you can use up both dienophiles. Otherwise, only one side is going to react. All right. So that's what this question is getting at. It's implying that you can do multiple cycloadditions based on the stoichiometry, right? If you got two dienophiles and two dienes, and keep in mind the dienophile is within the same molecule. So that's what I mean by two dienophiles. It's both alkenes in that molecule are susceptible to this reaction, right? So you got a molecule that contains two dienophiles, and then you got excess diene. Both of those dienophiles are going to end up reacting, right? But let's show it. So I won't cheat this time. I'll just rewrite it. So basically what's going to happen is this. So you get a diene on that side. That's not how it happens in reality, but I'm just drawing it this way. All right. And then if you number them, you're gonna get the same thing. 1, 2, 3. I'm back to kindergarten, back to square one. 2, 3, 4, 5, 6, and do the same thing on this side. 3, 4, 5, 6. Can you see it coming? Is it becoming clear what's going to happen? Right, your
Yes.
reaction. Yeah, your reaction is going to happen here. Oh, come on. Here and here, like so. And then you're gonna get the same thing on the other side. This is coming here. This is coming here and here, just like that. Right. So in the product, you're gonna actually see 2 6-membered rings. So you're gonna have a total of 3 6-membered rings in that product, right? This is not gonna change. So that's one side, and then the other side is gonna look identical to that. Y'all following that? Any questions about that problem right there? No questions? All right.
Nope.
All right, cool. Let me find one that is a little more challenging. There's one in here that I want to talk about. Oh yeah, we're gonna do 1656. And we're gonna do 1656, and we're gonna go up here, and let's take C and F and go ahead and knock those out. This is all retrosynthesis. So I'm gonna put that on a separate sheet. All right. So for C, when we do it, if we're working, again, the question asked what the start materials are, right? What diene and dienophile are needed to prepare the Diels-Alder product, right? So when we look at C, and again, this is a retrosynthesis, I'm gonna draw C out in 2D. That's what the 3D structure would look like, right? Do you see the bridge right here with the oxygen? Anytime you take a cyclic, either diene or dienophile, and an acyclic diene or dienophile, right? Cyclic meaning it's a ring, acyclic meaning it's not a ring. Take those, you're gonna get a bridged bicyclic system, right? That's all that is. It's a bicyclic because you have 2 rings. You got a 6-member ring, and then you have a 5-member ring, right? And then the bridge is where the oxygen is, like kind of connecting both sides, right? But I'm gonna write that out in 2D to make it, to simplify it. So we're gonna take that. We got a 6, we got a 5 with oxygen like that. And on the 6, we have 2 groups here. this is a good place to discuss one other topic too, dealing with what we call exo and endo. I'm gonna bring that up here. All right, so that's that. How would you break that apart? How would you retrosynthetically show how to get back to the starting materials? Where would you start? Anybody? Where would you start to do the retrosynthesis for this? What was the strategy I gave you when we talked about that?
Don't you have to break the bond?
Which bond? You're right. You do have to break a bond, but where do you
The
start?
alkene.
The alkene? Are you saying right here?
Alkene.
Yeah, you always start there. Always start there. Good, very good. Always start there. So we're going to push these electrons just like we would in the forward direction. It's still the same 6 electrons. It's the same 3 arrows. You're just getting a different result. So we're going to push the electrons like this. I'm going to do this. Right? And then remember, the bridge you don't touch. All right, so those sigma bonds, that looks like an S. Promise you. I'm gonna take an Oprah master class on handwriting. The bridge, you don't touch it. Those sigma bonds don't get broken, right? But you do, so you push that pair of electrons here. This other sigma bond over here, you're gonna break. And then this one, you're gonna end up breaking, right? Because that's your 6-member ring. If you can see that, you know the core structure for a 4+2 is a 6-member ring. So that's the 6-member ring. That's highlighted in orange. So that's all those are all the bonds you're dealing with. So you're gonna take this and move it here like that. And then you're gonna take this pair of electrons and move them here like that. So you're gonna break the pi bond and then 2 sigma bonds, which is exactly what you get going forward. You get a new pi bond and 2 new sigma bonds, right? So your 2 start materials are gonna look like this, right? This one is going to be here, like that. And the dienophile is gonna look like this. Right? Anybody not see that? Fix that up too. It looks a little sloppy.
No, I think I forgot to write in the H on mine, but I did get that product.
Okay. You're kind of breaking up, but I understood what you're saying.
I
So
just didn't write the H in.
you did it like that.
The second product.
Mm-hmm. So you showed it like that.
I didn't think we had to.
Yeah, you don't have to show it. You're right. If it's anytime you have a skeletal form, you don't have to show the hydrogen. But I just put it in just for the sake of clarity, of keeping track of everything. But you're right, you don't have to show that.
So any form is okay. Like
Yeah.
if you did it the first way you did it, and if you did it how you have it now, either form is acceptable.
That's fine. That's acceptable. Yes. Yep. So let me bring up one other topic dealing with this particular problem right here. So you can see in that too. Now this will give you some bias, but it's not the type of bias. Let me put it over here. Oh man. I just crop it. Hold up. 1 second. So with this particular product, if you notice, like that's one possibility, and you know, because there's no bias in the transition state, you also get another possibility, which is going to look like this. All right, so that's that. Mine's not as snazzy because it's handwritten, but the H will be here and the ester would be here. I'm just going to abbreviate it for space.
Are you showing us another way it could be written?
No. I'm showing you the other isomer.
Oh, okay.
Are you following? Because if you look at the product, if I were to do that here, I could say that for here, this is, well, let me draw it, get it right. All right, this will be back. I need to move that up. Sorry. So this would be back based on how it's written. And then the hydrogen will be up. Following? Based on the fact that the ester is down here. You see that? How the ester is shown pointed down.
Mm-hmm.
So if I wrote it in 2D and indicated the stereochemistry, it would look like that, where the ester would be on a dash and the hydrogen would be on a wedge. Yes,
Wouldn't the
no.
hydrogen always be?
Say again?
Wouldn't the hydrogen always be on the wedge?
Not necessarily, because remember, when I react these two together, right, there's nothing stopping both isomers from being formed, because that is a stereo center right there. Right? So I can get the other isomer, which will look like this. I'm gonna just go ahead and write the other 2D, other isomer in 2D. Right, where the hydrogen would be here and the ester would be here. Following? Yes, no, maybe. Right, because again, there's nothing stopping the one isomer being formed over the other.
I think I'm following.
All right. Any other questions about that part? So, because we can get it as clear as possible before I move on to this other concept. Because I don't want to lose you, have you lost in the sauce. When we
So the
talk about,
second one is just showing the opposite of what's on the first one, right?
yeah, the other isomers. So you got two stereoisomers possible.
Okay.
Did we do that up here? Right here, right? Then we showed them both here. We showed them in the first problem, second
Yes.
problem, same thing. So yeah, you're gonna get those stereoisomers are possible, right? But when you form these, let me finish writing that out because I know I'll forget when I get ready to post this. So you got two stereoisomers possible. All right. Both of them are formed. It's a racemic mixture, but when you make these bicyclic systems, there is a little bit of bias, and it's based on whether or not it's based on what this substituent is. Right. So I'm gonna write that isomer out in 3D, but I'm gonna expand out the ester so I can show you this other concept. All right, so here's my oxygen, and then I'm gonna write the ester out like this. Right, so that's this isomer right here, right? And then I can do the same thing with the other isomer. I'm just gonna copy it and paste it down here so we can compare them. right? So when you have these bicyclic systems, right, it's a there's a possibility if one of your substituents is a pi bond. We notice that the ester contains a pi bond, that this particular isomer that's shown, which we call the endo isomer, is favored. This isomer over here, we will call the exo. And it all has to do with how that bicyclic system, do you see kind of how it looks like a house? This is my rudimentary way of explaining it. Can you see how the ring system kind of looks like a house? I always call it like a dog house, but it looks like a house, right? And so the pi bond, that's the substituent, can be in the house or under the house. That's endo, meaning inside, which you can see right here, or it can be outside the house, like what's shown right here. All right, so this is I'm gonna say under the house. Or we're gonna be hood about it. It's indoors and outdoors, endo, outdoor. Y'all get it later. But this is under the house, and this is outside the house. Right? And so for these bicyclic bridge systems, the endo is always going to be favored over the exo. There's a reason for that too. I'm going to talk about that in a second. But before I do, are there any questions about that? That's a really special set of circumstances for that to happen, right? So one of your, go ahead.
The difference between the endo and the exo is just the structure of the substituents.
Yeah, the stereochemistry of the substituents, yes.
Okay.
But your substituent, in order for you to observe this, that substituent has to have some type of pi bond, right? I'm gonna put that in down here in a different color. Right, the substituent on your dienophile. Move that. Right, so your dienophile substituent must contain a pi bond in order to observe that endo-exo phenomenon. Right, so that's one criteria. The second one is that it's got to be like a bicyclic system, like the one we have shown, right? A bridged bicyclic system. So a bridged bicyclic. That's when you see endo and exo. And the reason the endo is favored is if I put in the pi bonds here, or well, the p orbitals, and then I put the p orbitals here on this, there's actually a little bit of overlap that can happen. And that's anytime you get orbital overlap, it's a stabilizing effect. All right, so you get a little overlap here and a little overlap here. Right. So endo is favored because of that p orbital overlap. Right. There's a technical name for it. We call it secondary orbital overlap, but that's why the endo is favored, because the pi bond on the substituent can overlap with the pi bond that's in your bicyclic system. Right, that's why endo is favored over exo. So I'm gonna put that down here in a different color. So endo is favored due to what we call secondary orbital overlap or orbital interactions.
So Dr. Russell,
Yes.
the endos, they're gonna always be, and the endo and the exo will always be set up the same, like the substituents. Like I know it won't be the same substituents, but will they always be set up the same? Like how you said the endo is like under the house, like it's like
Yeah. That's what the term comes from. So endo is just, it'll always look like that, right? Where that pi substituent is going to be underneath that ring system. Then exo is going to be outside, right? It's really short for endocyclic and exocyclic, right? Under the cycle and then outside the cycle. So it's endocyclic and exocyclic. But we just shorten it down to endo and exo, which is fine. But the only time you see that, again, is if you have a bridged bicyclic system and if you have a substituent on your dienophile that contains a pi bond, right? That doesn't react. Because you know the alkene is a pi bond also, but that's actually participating in the reaction. But the ester pi bond doesn't.
Dr. Russell,
Mm-hmm.
can you go down a bit?
Oh, yeah. Yeah, I'll scroll out or zoom out. All right, any other questions about that?
All right, I'm good.
All right. All right. Man, it's 9:45. Wow. All right, let's do F real quick. I'm gonna see if I can copy that because I have to put down another page. Well, we're not out of room. All right, so F again, we're just doing retrosynthesis. All right, how would you break F apart? What would that look like?
You break the
Gotta break
alkene.
the pi bond.
Right here. Always, that's the strategy for retrosynthesis of Diels-Alder products. Right. All we've been talking about is 4+2 cycloaddition. So the strategy is to start at the alkene every time. So I'm going to take this pair of electrons and move them here. And then and then again, these are the only bonds I'm working with. This 6-member ring right here. I'm not touching anything else. All bonds that are broken and made to go backwards or broken to go backwards, we only use those bonds that are within that 6-member ring system. We don't touch any of the other bonds, right? So that's that. And then I'm going to break this bond here, boom, like that. And I'm going to break that bond right there. Any questions about that?
No, you were breaking the pi bond, like the alkene, and then you broke the sigma bonds, right?
Yes. And that happens. That's my strategy for retrosynthesis of 4+2 cycloaddition products. I start at the pi bond and I work my way around that 6-member ring. Right? So the dienophile is going to look like this. I think we can all kind of agree on that. Boom, like that, and then like that, right? Is that right?
Yes.
And then my diene, probably gonna need to move that dienophile over. My diene is going to look like this. Like that. Is that right? Isn't that what this indicates over here? I'm going to put a pi bond here. I'll put a pi bond here. Is that right? And then I'm going to break.
Yes.
I'm going to break this sigma bond right here. And I'm going to break this sigma bond right here. And I'm going to put a pi bond here also. All right. We're following?
Yes.
All right. All right. One more, since I had planned to not do this the whole class, but it's all gravy. I think we needed it. And I think y'all are catching on too, so that's good. That's more important to me than rushing. There's one more problem I want to talk about, and that's 1656. So I'm gonna copy it and paste it on a new page. How did it get up there? Yeah. All right. Let me put this here. All right. So if we read this question, it says, what is the structure of the product formed when A is heated in the presence of maleic acid? All right. And then it says, explain why only one product is formed, even though A has 4 double bonds. All right. So let's work through a process of elimination. Right. A is the diene, right? This is the dienophile. That's the dienophile. Everybody agree with that?
Yes.
Okay. And then, so this is my diene. Remember, if you're doing a 4+2, your diene has to be conjugated, right? There's two criteria for your diene. It has to be conjugated, and it has to be able to adopt the S-cis conformation. Those are the 2 premises we're working off of with this problem. So it must be S-cis. So it's got to be conjugated, and it's got to be S-cis. All right. So let's see what we can rule out, and then we'll come back and see what we can keep, and that's where we're going to start from. So you can see a kind of a pattern of a diene down here. Is that right?
Yes.
What's the problem? What's wrong with it? Look at the 2 criteria. Which one?
It's not conjugated.
Not conjugated, and it can't be S-cis anyway because it's a ring system. So this is out. Right? It's not conjugated, and it's not a ring. I mean, it's not a ring. It's not able to adopt S-cis. Right? Now we got another diene up top. Right here. It's conjugated for sure. Is that right?
Yes.
It's definitely conjugated, but the fact that it's in a ring means that it's locked in S-trans, so we can't use that either. So that ring kind of forces that in, that S-trans, it holds it. You can't roll. And how do you go from S-trans to S-cis? Let's see if anybody remembers that. What do you have to do? How do you get from here to here? What do you have to do?
Don't you got to move the bond?
How though? How would you move it? You're right. I agree with you 1,000%. But how would you move it? Right? How would you get this? Let me see which one. I moved this one. So how would I move this bond around to the other side like it is on the right? right here. All right. For the sake of time, I just rotate around that sigma bond. That's how I get from S trans to S cis, is by rotating around that sigma bond. And it does cost some energy, but again, that's why you do the reactions at high temperature. So you can have enough energy available for that little equilibrium between S trans and S cis to be towards the S cis side. So that sigma bond that's holding those two pi bonds together, that's compressed because of the overlap between the two the carbons here and here, right? When we talked about that, you can rotate around that bond. Here, you see the sigma bond right here. You can see it, but you can't rotate around it because the ring blocks that conformation, right? So you can't do anything about that. So even though it's conjugated, it can't react because it's trapped in S trans, right? Now you got another diene right here. Right, and that one actually fits both criteria, doesn't it? It's conjugated and it's S trans. Is that right?
Yes, S cis.
Yeah, thank you. S cis. So this is the only diene that fits the criteria. Right, that's the only one. So that's why you only see one product. Right. So what would that product look like? Is it going to be bicyclic with a bridge? Let's see if we can draw it out in 2D. And then we'll worry about the 3D because we're running out of time. So that's one ring. It's two rings. And then my third ring is going to look like this. Do that. Yeah, it's going to be right there. Come on, Russell. Here, like that. Right, so it's going to be, and this is my bridge right here. Right, so the alkene is going to be actually on the bridge right here. And then this is going to be the acid here. Can y'all see that? So we're going to count from here. 1, 2, 3, 4, and then this is 5 and 6. Or you can put 5 and 6 the other way around. Right? But you're gonna have this tricyclic system and put all the other double bonds back in. Here and then here. All right, so that's what the product is going to look like. It's going to be a bicyclic system. And it just so happens that on the bridge, in this case, that's where your alkene is going to end up. Right, let me draw it out. So this is going to be your, I'm just going to forget about the rest of it. I'll just tack it on. It's going to be that plus this. But you can see here the diene is kind of inverted, right? It's not how we're used to seeing it. And so that's why that the bridge part is going to have that alkene in it. So you'll go basically, the electrons will be from here to here, like that. And then we'll push that there. So your product is going to have this 6-member ring like that. That's what my new alkene is. And then it's going to have that other 6-member ring. The larger ring is going to be here, like that. And then that's where your substituents will be. Right. So we got to stop because we got like a minute left. Any questions before we log out? And I'll post the notes and upload the video after my next class.
It's not, I have a question, but it's not regarding the material. So I had emailed you about the grades in the, on Blackboard, and you said that they'd be updated over the weekend. Were they updated or no? Not yet.
Well, no, I started working on it. I deleted some of the assignments and the exams that don't count, because with this Blackboard Ultra, like sometimes it'll count, it'll just have everything in the grade book counted as if it was going to count. So the class looks like it's worth like 4,000 points, but it's really not. It's really only going to be worth about either, I think it's like 900 to 1,000 points, including the homework, the quizzes, and the exams. And, you know, obviously the bonus work is not going to count against you. It'll only count for you. So I'm still working on deleting the stuff that's